So this is going to finish up chapter 16, just some finer points about acid base. First off is a mention of polarity versus how the hydrogen comes off in a acid situation. So if I'm looking at the halogens, HF, HCl, HBr, HI, the bond itself between H and F here is the most polar, while the bond in the HI is the least amount of polarity. So because of that, you will see that HF is considered a weak acid and these other ones are considered strong acids because it is the most polar, it's going to be harder for you to remove the H plus, okay? Because it is kind of tied into that F minus, that electron is much more closer to the fluorine than it is the H. So it doesn't really want to pop off. While HI completely dissociates, so it wants to lose the H plus completely. Okay, so so you can look at polarity to figure out how strong of an acid it's going to be. So oxyacids, another topic kind of brought to in the book, is acids with OH groups attached to what we call a central atom. So there's going to be different ways of you to look at these oxyacids, and do note that that H is acidic H. Okay, so it's not a alcohol group that we're talking about. So what happens if you have a different central atom for this? So I'm going to pause the video and draw a couple examples here. So I drew H2SO4, so please understand that sulfur is in the middle and you have the 4 oxygens around it, and then the hydrogens directly attached to the 2 oxygens. What we're focused on is the hydrogens that pop off here. And then I drew H3PO4, and again, these are the what we call acidic hydrogens attached to the oxygen. So what we want to look at is the central atom, and it's what we call its electronegativity. So sulfur has 2.5 as its electronegativity, phosphorus is 2.1. So I'm going to draw the bond between sulfur, oxygen, and hydrogen down here. I'm going to make this a little bigger so you can kind of see it a little closer. All right, so sulfur attached to oxygen to hydrogen. So again, oxygen has a 3.5 as their electronegativity, sulfur is 2.5. And so those electrons are going to be pulled towards the oxygen, okay? And the difference between these two is 1, okay? So if I compare that to phosphorus, oxygen, and hydrogen, phosphorus is 2.1, this is 3.5. So the difference here is going to be 1.4. So it's a bigger difference. So because it's a bigger difference, this hydrogen is going to hold on more because of the electronegativity difference, while this one is going to pop off. And this is, again, considered to be a strong acid with that first hydrogen that comes off. So when you have a central atom, and you're comparing both central atoms, okay? The one with the greater electronegativity, okay, and you're going to base it off of how close it is to fluorine, okay, is going to be the stronger acid, okay? So again, because sulfur has a bigger electronegativity of 2.5, the difference between the sulfur and the oxygen is smaller. So that means it's going to be easier for this hydrogen to pop off. While if I have phosphorus, because there's such a huge difference here, that pull is going to keep that hydrogen on that oxygen. So again, the rule is that central atom, the greater electronegativity is going to be the stronger acid. Now, if you have the same central atom, okay, The strength is going to increase based on the number of oxygens, So the easy one for this one is this grouping here. And I'm going to write an additional one, which is HClO, which has a number 3 times 10 to the eighth. So if you want to write that in. So HClO4 is considered to be a strong acid. So you really don't have a Ka value. Well, if you pop off one oxygen, you still have a large Ka, so that's why sometimes HClO3 is considered to be a strong acid. In our world, it's going to be considered a weak acid. HClO2 has a Ka value of 1.2 times 10 to the second. And then HClO, finally ripping off the last oxygen, is 3 times 10 to the negative eighth. So the more oxygens you have, okay, in your molecule, the more you have the density of the electrons. So you have a stronger density core. So because the chlorine and that oxygen, that relationship is going to pull in on those electrons, that hydrogen is going to pop off pretty easily. So the more oxygens you have, the more it's going to increase the likelihood of it being strong, or more chance for the hydrogen to come off. Because even if you look at your Ka values here, you will see even with HClO3, you have a very large Ka here. So a lot of the H comes off. And that's pretty much done with oxyacids. I do want to mention carboxylic acid. Again, acetic acid is our example. I just want to reiterate the different ways you could write acetic acid is the COOH variety. And that's because if I look at acetic acid in terms of its structure organically, okay, I will see that it has a C double bond OOH, and this is the acidic hydrogen. Okay, that's the acidic hydrogen. So I just like to point that out because, again, we did talk about some organic chemistry at the beginning, and you sometimes see acetic acid written this way because you have the COOH. That is essentially this part of the molecule. So just to kind of reiterate that. All right, and finally, a good rule of thumb for anything that is an oxide, meaning it has oxygen in it, if you have nonmetals attached to oxygen, they're going to be considered acidic. So that is why you see with these two examples, I produce H2SO3 and H2CO3. Because again, this undergoes its own equilibrium and produces H3O plus in water and HSO3 minus. So anytime you have a nonmetal attached to oxygen, you're going to consider it acidic. If you see a metal attached, so again, this is calcium oxide, this is magnesium oxide, those are going to make what we call a basic solution. And again, once you make calcium hydroxide, it's then going to act more of a strong base, and so is magnesium hydroxide as well. Okay, so you will see I have the arrows only pointing in one direction there because we are assuming that those are acting more as a strong base component. So not much emphasis anymore on you knowing acids, oxides specifically, but I kind of throw them in there, especially for something like H2CO3. Carbon dioxide bubbling through water is going to make it acidic. And that's why you need to be careful of exposing water to air for a period of time, because it probably is going to make it slightly acidic.